let's review from the last time we were together. How many protons, neutrons, and electrons are in an atom of boron 10? So hopefully you know now to pause it and do this, and then we go through the answer. So let's see. There are 5 protons because the atomic number is Z. There are 5 electrons because there's no charge here. And 10 minus 5 is 5, so there are 5 neutrons. Starting now, we're going to talk about the mole. A mole is a unit. So another unit that we kind of make up, right? But not really. So we're going to look through this one. It's not that we just make up these units willy-nilly. They are well thought out and mathematically represent specific numbers. So atoms are very, very, very small. We can't see them without microscopes and very high-level instrumentation. So we need to be able to count how much we have without being able to see it. So if we can see the amount of a substance that we're working with in a lab, there are enormous amounts of atoms in that substance. So a mole is a unit. So how many atoms are in a mole? This is where we talk about Avogadro's number. So this scientist named Avogadro discovered it. And he said that 1 mole of anything is 6.022141 times 10 to the 23rd of anything. So I can have 1 mole of students, but I would go insane because I would have 6.02 times 10 to the 23rd. That's a lot of students, okay? So that's a lot of students. I don't want to have that much grading to do. I would probably say no thank you. I could have a mole of desks. I could have a mole of paper. I can have a mole of anything. But in chemistry, we have a mole of particles. So particles is an umbrella term. And under that umbrella, we use the terms ions or molecules or formula units. What else could I have? Molecules, ions, formula units. That's good for now. But these are just certain terms that we use more commonly in chemistry. So you're going to have to be able to understand these terms and what they mean in order to be able to do the chemistry. So the chemistry, this is our counting number. So we don't have to remember to write this whole times 10 to the 23rd of things. We're going to make it easier and use the mole. This is our counting number. Again, just like a dozen is 12, a mole is 6.02 times 10 to the 23rd, and you're going to want to know that number. So Avogadro's number, it's often abbreviated as capital N, subscript A. It means 1 mole of any element contains 6.02 times 10 to the 23rd atoms. That's what I forgot, was atoms under our umbrella. 1 mole of anything. So of an element, if we're going to use the term atoms, atoms refer to an element, meaning it must be on the periodic table. If we're referring to a molecule, it needs to be a molecular compound. We haven't really talked about all this yet, but that means that that compound shares its electrons when they form the compound. An ionic compound is called a formula unit, and they transfer electrons when they form a compound. And we could have cations or anions that go with those, and that would be part of this would be a positively charged compound, and this would be a negatively charged compound. This is a picture of 1 mole of a bunch of different substances. You can see helium takes up quite a bit of space here. It's 1 mole. only has a mass of 4.003 grams. Mercury, 200.6 grams per mole. Sulfur, 32.07 grams per mole. And copper, 63.55 grams per mole. You can find those numbers on the periodic table. These are the average atomic mass that we calculated earlier. But instead of having to calculate them for compounds from using the natural abundances and all of that, we can actually add our compounds together using the average atomic mass from the periodic table. Now, if you remember, that was an AMU. And if you remember back, I had you take 1 divided by 1.66 times 10 to the negative 24th in your calculator, and you got 6.02 something 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 times 10 to the 23rd, because they are related. And since they are related, we can use this interchangeably. We can say 1 AMU is equivalent to 1 gram per mole. Now, I'm going to be a stickler on this, and I should, because this is going to be very important. It's not grams. It's got to be grams per mole, because we have to take into account that Avogadro's number. Otherwise, it's not equivalent. So it is grams per mole, not just grams, and you will lose points if you just put grams. So what is molar mass? And your notes might be a little out of order because I moved these around. I can't remember, so you might just want to look a couple ahead if this isn't in the right spot. But molar mass is the mass in grams of 1 mole of a substance. So we can actually, if we looked on the other page and we saw sulfur has 32, right here, 32.07 grams of sulfur is equal to 1 mole of sulfur. So we can write it like that, and a lot of you can see that that can be a conversion factor that we can convert between grams and moles. The molar mass of 1 mole of carbon-12 is exactly 12 because this is based off of carbon-12. Molar mass is numerically equal to its atomic mass because of what we just talked about, because AMU through Avogadro's number is related to grams per mole. Remember, per mole is important. So the atomic mass and the molar mass for calcium, the atomic mass, the units are AMU, 40.08 AMU. Molar mass, the units are grams per mole. Even though these are equivalent, if I ask you for the molar mass, you must put grams per mole. If I ask you for the atomic mass, you need to put AMU. So you need to understand the difference and when to use the proper unit. Molar mass is a conversion factor we can use to go from grams of a substance in the lab to moles, to particles, and a whole bunch of other things that we can go to. So moles is going to be where we want to get to. How do we calculate molar mass? So you need to have your periodic table out. If you don't have it out, then you're not going to be able to do this with me, so you need to go get it. We want to calculate the molar mass of carbon dioxide. So to do that, we need to look at how many of each of these elements are here. We have 1 carbon and 2 oxygens. So you need to look on your periodic table and say, what is the molar mass of carbon? And you should get 12.01. So we have 1, and I used the non-rounded periodic table, so don't worry if it's a little bit more numbers than yours. 1 times 12.0107 gives me 12.0107. That's just for the carbon. Now I have 2 of the oxygens, so 2 times 15.9994 gives me 31.9988. Now I'm going to add both of these together to get 44.0095 grams per mole. So this is the molar mass. Why don't you pause it and try the next one before we do it together? Glucose, we have 6 carbon, 12 hydrogen, and 6 oxygen. The molar mass of carbon is 12.0107. I have 6 of them. 6 times 12.0107 is 72.0642. I take 12 times the mass of hydrogen, so 12 times 1.00794 is 12.09528. And 6 times the mass of oxygen of 15.9994 gives me 95.9964 grams per mole. When I add all of those together, I get 180.1559 grams per mole. So this is the molar mass of glucose. I want you to pause and try each of these. So I'm going to give you the answers now because you paused it and tried it, but if you didn't, you need to go back and figure out how they came about. But one thing to note, in this formula like this one, this means there are 3 bariums. But because these parentheses are here, I have 2 times 4 oxygens and 2 times 1 phosphorus, giving me 2 phosphorus and 8 oxygen for that one. So there are the answers. You can always ask questions, obviously, if you got them wrong or try to figure it out what happened. So once we can figure out how to get from grams to moles, we can go other places. So moles are our oyster, essentially. Once we get there, we can go anywhere. The number of moles, we can go to atoms, molecules, formula units. So calculate the number of atoms in 4.50 moles of silicon. So I'm always going to start with these problems right now. What's given? 4.50 moles of silicon. For every 1 mole of silicon, how many atoms do I have? Well, moles to atoms, particles to atoms requires Avogadro's number. So I'm going to say there are 6.02 times 10 to the 23rd atoms of silicon. I'm going to click over because it's on the next slide. I work it out. So here we get 2.709 times 10 to the 24th. When we round that to the proper number of significant figures, here I have 3 sig figs, and this is 3 sig figs total. So this is my final answer. This says how many moles of silicon are in 2.45 times 10 to the 24th. So now we're saying that atoms of silicon, we have this many atoms. How many moles do we have? So I take the 2.45 times 10 to the 45th atoms, my multiplication sign in a line. Remember, this is just dimensional analysis. I want to get rid of atoms, so I put them on the bottom. And I want to go to moles of silicon. So atoms cancel. We put Avogadro's number with the atoms. 1 goes with the mole, and we calculate that to get 4.069767442 times 10 to the 21st. 3 significant figures, 1, 2, 3. We look 1 to the right for rounding. It's a 9. It's going to round that up to a 7. So 4.07 times 10 to the 21st moles of silicon. So this is the part we just did. So we used Avogadro's number here. Now we're going to look at this part where we can go between grams and moles, and this is where we need to use molar mass. Determine the number of moles in 85 grams of sodium chlorate. So I gave you the formula for sodium chlorate. You're going to want to say, okay, let's see, 85 grams of NaClO3. So we need the mass of sodium chlorate. So we need to take 22.99 plus chlorine, which is 35.45, plus 3 times 15.9994, giving us 106.4382. I'm actually going to erase this. So 106.44 grams per mole. So the grams go in the bottom because I want to get rid of them. Here they are, and here they are. Opposites cancel. Moles are in the top. We're going to divide the 85 by 106.44 to get 0.7985719,654. We can have 4 significant figures because this is 4 sig figs. We look here, 1, 2, 3, 4. 1 to the right for rounding. It's a 7, so we'll round up to get 0.7986 moles of sodium chlorate. So not bad, we just got to remember what's being asked of and what to do. The math itself is relatively simple. Determine the number of grams in 3.90 times 10 to the negative 4th moles of magnesium fluoride. And you don't know this yet, but magnesium fluoride has this formula, MgF2, and that's an F. So some of you covered naming in your previous chemistry course and some of you haven't. So MgF2 has that formula. Pause it and try it. So we start with the 3.9 times 10 to the negative 4th moles of magnesium fluoride. We want to get rid of moles of magnesium fluoride. We say 1 mole of magnesium fluoride is equivalent to 62.31 grams of magnesium fluoride. This is the molar mass, just put into dimensional analysis. When we multiply by that in the calculator, we get 0.024309. We can have 3 significant figures. 1, 2, 3. We look 1 to the right for rounding. Remember, these don't count. So 0.0243 grams, or 2.43 times 10 to the negative 2nd grams of magnesium fluoride. Number with the correct number of sig figs, unit, and label are all very important for a full credit answer. Moles to molecules. So determine the number of molecules. Molecules is a particle term. So you should be asking yourself what type of number I might need to use. In 4.6 moles of ethanol. So we're starting with 4.6 moles of ethanol. And we want to get rid of moles and go to molecules. So what do we need to do now? 1 and 6.02 times 10 to the 23rd. So this is an Avogadro's number problem. When we calculate that, we get 2.7692 times 10 to the 24th, 2 significant figures, 1, 2. Look 1 to the right, it's a 6, giving us 2.8 times 10 to the 24th molecules of ethanol. So number to the proper sig figs, unit, and label for a full credit answer. If you have 2.17 moles of tin 4 fluoride, how many formula units does it have? Formula units is a particle term. Since it's a particle term, it's saying how many of these individually that we have stuck together. We start with the 2.17 moles of tin 4 fluoride. We put moles on the bottom because we want to get rid of it. And formula units goes on the top. Now you can write formula units as long as it's not personal. I will accept that, but I won't write that. I'm going to write form unit because I don't want to offend anyone. Okay, so how many formula units? 1 mole is 6.02 times 10 to the 23rd. So this is an Avogadro's number problem. We do that math and we get 1.30634 times 10 to the 24th. We round that to 3 significant figures. This is 3 sig figs here. 1, 2, 3, 1 to the right for rounding. And we get 1.31 times 10 to the 24th formula units of tin 4 fluoride. Moles to formula units. Again. So try it. Pause it. Try it. Okay. We have 8.42 times 10 to the 24th formula units of silver nitrate. How many moles do you have? We're going to start with the 8.42 that's given. We want to get rid of the formula units. We put Avogadro's number on the bottom. We do the math by dividing by Avogadro's number and we get 13.98671096. We have 3 sig figs here. 1, 2, 3. We look 1 to the right for rounding, giving us 14.0 moles of silver nitrate. Put it all together. How many molecules are in 454 grams of water? So this is the first two-step process we have. 454 grams of water. We need to calculate the molar mass of water. So depending on which periodic table you're using, you'll take 2 times the mass of hydrogen, 1.00794, plus 15.9994, and you get 18.016. So 18.016 grams of water for 1 mole of water. This is the molar mass step. My grams cancel, and I want to go from moles of water to molecules of water. 1 with moles, I'm going to look at the molecules. That's Avogadro's number, 6.02 times 10 to the 23rd. Molecules of water. Moles cancel, and we're going to do the math. So let's do the math. Again, grams cancel, moles cancel, and we get 1.517029307 times 10 to the 25th. Now 3 sig figs here. 1, 2, 3. 1 to the right for rounding gives us 1.52 times 10 to the 25th molecules of water. Don't round until the end. Even if you decide to do this in a two-step process, don't round until the end so you don't have rounding errors. Good, I hope it's going well. Obviously, we can't ask questions until we get together, so I'm just going to keep going. Practice, try it, pause it, try it, please. How many grams of hydrochloric acid are there in 5.71 times 10 to the 22nd molecules of hydrochloric acid? So we want to go from molecules to grams, but first we have to go to moles. So 6.02 times 10 to the 23rd goes with molecules. 1 goes with moles. And for every 1 mole of HCl, it has a mass of 36.458 grams of HCl. Rarely will I give you a molar mass, so just to home that point. I'm going to erase this. End up with 3.458059468. 3 significant figures. 1, 2, 3. 1 to the right for rounding gives me 3.46 grams of hydrochloric acid as my answer. How many hydrogen atoms are there in 4.6 moles of ethanol? I'm asking you a different question this time. So this time we're going to go, we have moles. We want to go from moles to atoms, but not just atoms. We want to go to hydrogen atoms. And remember, if you have the word atoms, it has to go with an element, and ethanol is not an element. So first we need to go either, well, there's more than one way to skin this cat, but I'm going to say there's, we're going to go to molecules first, and then from molecules to atoms of hydrogen. So why do you think they write this formula this way? Is it just to confuse you? Do you say like, oh, if we put the hydrogens in different places, they won't know how to count them? No, because this tells me that I have this structure. So it's called the structural formula. And it tells me I have an alcohol group on there, so that this is an alcohol, because there's other ways that you could put this together that wouldn't be the same if I wrote that together, that maybe it could be an ether. But they both have the same formula, but these are not the same functional group. This is called an ether, and this is an alcohol. So they have different properties. So they write it that way so you know you're talking about this molecule and not this one. So when you take organic chem, there's a lot of different molecules that have the same chemical formula. They're called isomers, and that's why they write it like that. So that's a structural formula. It tells you a little bit about the structure. So we're starting with 4.6 moles of ethanol, C2H5OH. we want to go from moles of ethanol to molecules of ethanol. Because we want to go to atoms eventually, and we're not there, we want to go from molecules of ethanol to atoms of hydrogen. Okay, so in 4.6 moles, we have 1 mole, because remember the 1 always goes with moles, to 6.02 times 10 to the 23rd molecules of ethanol. Now that we're in molecules of ethanol, they're saying for every one of these that I drew out, sorry, my drawing is a little off here. So for every one of these that I drew out, this is 1 molecule. So in that molecule, in one of these molecules, how many hydrogen atoms do I have? 1, 2, 3, 4, 5, 6. Do you have to be able to draw it out to know that? No. 1, 2, 3, 4, 5, 6. So you can just add them up. You don't have to be able to draw it. I just wanted to draw it to show you how it works. So we look at that and we say for every 1 molecule I have 6 atoms of hydrogen. Calculate it, 1.66152 times 10 to the 25th. 2 significant figures, 1, 2. Look 1 to the right for rounding, gives us 1.7 times 10 to the 25th hydrogen atoms. This one is worded a little differently. What is the mass in grams of a single atom of nickel? Well, if you look on the periodic table, you're going to find out the mass of nickel is 58.69. And what are the units? Grams per mole. We now have the mass in grams, but we have the mass in grams per mole. We want that for a single atom. So this question tests, do you know what the units are on the periodic table? Do you know how to convert them? So we need to take that 58.69 and convert it from per mole to per atom. Go ahead and give it a try. Pause it. 58.69 grams of nickel per 1 mole of nickel. I want to get rid of moles of nickel to go to per atom, so I'm going to divide by Avogadro's number. I get 9.74916944 times 10 to the negative 23rd. I can have, according to this periodic table, 4 sig figs. 1, 2, 3, 4. I look 1 to the right for rounding. It's a 1, so I'm going to leave it alone. 7.49 times 10 to the negative 23rd grams per atom of nickel. So really not too bad, just got to make sure we know what is being asked of us, right? So if you get the question and you have no idea, usually the first thing is how do you get to moles? But in something like this, we're testing, do you know what units you have on the periodic table? So that can be where you start too. All right, determine the number of fluorine atoms if in 24.24 grams of sulfur hexafluoride. Sulfur hexafluoride is SF6. Pause it and try it. Now I'm going to go through it right now, so if you didn't pause it, you're losing out. So we're going to start with the 24.24 grams. We're going to go from grams to moles of SF6. So grams of SF6 to moles of SF6. And then from moles of SF6 to molecules of SF6. And from molecules of SF6 to atoms of fluorine. So we start with the 24.24. We have grams. We get the molar mass. We go from moles of SF6 to molecules of SF6. And for every 1 molecule of SF6, we have 6 fluorine atoms. When we do that, we get 5.994. We have 4 sig figs here. So 1, 2, 3, 4. Look 1 to the right for rounding. 5.994 times 10 to the 23rd fluorine atoms. Make sure to practice this. This will be on every test quiz and all the way up through the final.